C9, Cartesian coordinates and the matrix of representation. We have three vectors, magnitude A, B, and C. Direction is along the x, y, and z axis. X-axis, y-axis, and z-axis. Okay. Find the right triangles. So x, y, z axes are perpendicular to each other. So E1 dot, E2 equals 0, E2 dot E3 equals 0, E3 dot E1 equals 0. So this one means a cosine half of pi. The angle between any two are 0. By the way, I have replaced the file. I modified this file and uploaded it to the Blackboard. Please refer to the revised version. Find the right triangles. A triangle, one angle with a single angle is a right angle. We say it's a right triangle. So for example, x-axis and y-axis, they are perpendicular to each other. This is a right angle, so OAB is a triangle. OAB is a right triangle. Okay, OBC, OBC. This plane, xy plane, and z-axis, they are perpendicular to each other. So any straight line on this plane and the z-axis, they are right triangle. So this is also a right triangle. Okay. OAC, OAC. So it looks slanted, however, still YZ plane is perpendicular to the x-axis. Therefore, this straight line and this straight line, they make a right angle. So this is also a right triangle. There are many other. Find A dot B, B dot C, and C dot A. We remember A is parallel to E1, B is parallel to E2, and C is parallel to E3. Therefore, all of them are perpendicular to each other. As a result, everything equals 0. What is the way of proving the Pythagoras theorem with Cartesian coordinates? So Descartes contributed a lot. So Cartesian coordinates, we have Cartesian basis vector to make the proof of Pythagoras theorem very, very easy in comparison with what we learned directly from the Euclidean geometry we learned in middle school. It's trivial. For example, we have A, B, B, C, C, A. All of them are 0. Why don't we compute A plus B squared? The absolute value of they are perpendicular to each other. A and B are perpendicular to each other. And this is A plus B vector. So they are connected. Head and tail, head of A and tail of B are connected. So this is the diagonal. So this hypotenuse of this right triangle, so A plus B squared, can be computed as a scalar product of A plus B and itself. Therefore, if I expand this one, I can find A squared A squared, B squared, and AB, BA. There are two, A dot B plus B dot A, and they are commutative. So we have A squared, B squared, 2AB. However, we know A and B are perpendicular to each other. This vanish. This term vanishes. Therefore, we have found that the magnitude of the hypotenuse of this triangle is square root of a squared plus b squared. This is the Pythagoras theorem. So it's a trivial algebraic calculation reproduces Pythagoras theorem. So we say analytic geometry reproduces Euclidean geometry. So we can do anything regarding the geometric problem with algebraic problem. So this is Descartes' work. Okay, what is the length of a plus b plus c? Remember, this is a plus b plus c. What's that? A vector, b vector, c vector. Sum of these three vectors is a diagonal of this parallel pipe. So this is a straight line. And remember, this one is a hypotenuse of this right triangle. So I can compute this magnitude using the Pythagoras theorem twice. For example, this length is a, b, and we have a squared plus b squared square root because it is a right triangle. And then this is also another right triangle. And we can draw this. This is square root a squared plus b squared. And this one is a c, and this is a right triangle. As a result, this one is a squared plus b squared plus c squared. So application twice, we apply Pythagoras theorem twice to obtain this result. However, we can directly prove this by computing the square root of a plus b plus c squared. As we have done here, we can expand and we find every crossing term vanishes. 2. Compute the area of a triangle in terms of the scalar products. Okay, area of a triangle, this I'm computing the area of this triangle. So easiest way is base. We choose this one as a base, and this is height. What is the height? This is the height. That is the B's component that is perpendicular to A. Okay, so we say this is B perp. So area is base times height, A magnitude, and B perp magnitude multiplied by 1/2. So B perp magnitude is a B vector magnitude sine theta. Or this sine theta can be computed square root 1 minus cosine square theta, because we know Pythagoras theorem. Okay, so in this manner, we can decompose any vector B as a sum of two components that are parallel to A. A is here. Parallel to A, that is called the B parallel vector. This is B vector. Perpendicular component that is perpendicular to A. So I denote this one by B perp. So parallel component can be read out by making use of the completeness relation in one dimension. So B parallel is identical to its vector, unit vector along the A direction. So this is a Cartesian component, and this is the unit vector. We can revive the full expression that is A divided by magnitude of A. So substitute this for this A hat to find that A B dot A and A appear twice in the numerator, but we are projecting out the direction only, so magnitude squared is divided. So in either way, you can compute the parallel component of a B vector that is parallel to A. I can make use of this to find out the B perp. That B perp can be obtained by subtracting B by B parallel. So I copy this B parallel here to compute the perpendicular component. So it can be denominators can be combined like that. As I already told you, area of a triangle is 1/2 base times height. And the height is the magnitude of B multiplied by sine theta. All right, so we recall that cosine theta can be computed by taking this ratio of the scalar product of A and B divided by the product of the magnitudes. Therefore, we have sine theta is magnitude of B perp divided by magnitude of B, and that can be re-expressed in terms of the Pythagoras theorem, and substituting this cosine theta in here, I can express like that. And as a result, we can compute the area of a triangle, this expressed in terms of the sine theta, angle theta, but this can be expressed as this form. Okay, or this, the same. We shall find that this is identical to the 1/2 of cross product squared. 3 Cartesian components of a vector are particularly useful when we employ matrix representation. We need to learn very carefully. A vector can be expressed as a linear combination of the 3 components, the x, y, z components. And we call these are Cartesian components, and E1, 2, 3 are the unit basis vector of the Cartesian coordinate system. From middle school on, or perhaps in the elementary school, you learned the ordered pair of numbers x comma y, something like that. So this is nothing but a matrix representation. Usually we use the comma, but we use some space, erase a comma, and I can copy the Cartesian coordinates in order: x component, y component, and z component. So we call the list, this kind of ordered list, is a row, a vector. So I can let it stand up. We call it a column vector. Column vector, and this is a row vector. And there is a rule: lay down to this form and stand up to this form. This kind of transformation, the making a column to row and make a row to a column, we call it as a transpose. And we attach a superscript, capital T, to represent the operation to replace the column to row and row to column. We recall that the scalar product of A and B using Cartesian coordinate, it is 1, 1, 2, 2, 3, 3. So matrix representation is naturally introduced to express this busy expression in terms of a compact form. So this is just our, we define this guy to be identical to this. So it looks busy. It looks busy. But this summation indicates that A1, B1, A2, B2, A3, B3 are all summed, right? This notation indicates that here I always write a row, and here I always write a column. Either way, row first and then column. And if I have one row and column, this one is the matrix multiplication. Matrix multiplication. So this multiplication is this. How can I compute this? First element, product. Second element, product. Here. Third product. And sum them all. We know this operation, scalar product, is commutative. B dot A equals A dot B. Therefore, this one can also be expressed as I runs from 1 to 3, BI, AI. So this one and this one, they are the same. Therefore, I can make an operation. What kind of operation? That I just told you, transpose operation. This one, transpose is let it be a row. So if a column becomes a row, there is no way but to put it on here. If I replace this one with a transpose, the row becomes a column, and I told you row always appears in front of a column. Therefore, this row becomes a column, and that column should be written on the right side of a row. So, in general, the matrix product transpose is always they are upside down, but this is based on the very simple fact that scalar product is commutative. Okay. A row vector and a corresponding row vector and column vector, they are called mutually transposed. A row becomes a column and column becomes a row. We say they are mutually transposed or conjugate. So we have, for example, square root of 2 plus 1 and square root of 2 minus 1. They are called conjugate. If I multiply square root of 2 square minus 1, 2 minus 1 equals 1. A plus bi, they have conjugate. They are pair. If I multiply them, I have a square plus a b square, something like that. These kind of pairs are usually called conjugate. So this row and column, they are mutually transposed and they are conjugate. We also say they are dual. They are equivalent. By the way, if I compute the the self-scalar product, then identical row and identical column appears. Okay, we generalize this one, this multiplication of two row and column with the same 1, 2, 3 elements. 1, 2, 3 elements. The number of elements must be the same when I want to multiply row and column. So we generalize this to a more complicated form, but it's a trivial. A matrix is called this kind of list of numbers. For example, these number, I can transpose this. Transpose. What happens? Row becomes a column. You can find these elements are written in here. Okay? second row, the subscript usually stands for the entry of the element. So first row, first column, first row, second column, first row, nth column, second row, first column, second, nth, mth, first, mth, second, nth, something like that. And if we take the transpose, the row becomes column, row becomes column, row becomes column. And when we want to compute the product of two matrices, the rule of multiplication is basically identical to what we have done with the scalar product. Therefore, multiplication can be, it looks very complicated, but it is easy if I just encircle a row and insert a column. By the way, we remember A1, A2, A3, and B1, B2, B3 is nothing but the scalar product. However, I can insert an identity matrix. Let's see this identity matrix, and we multiply B1, B2, B3. So that is identity multiplied by B1, B2, B3. What's that? Row and column. If I multiply everything, B1 plus 0 plus 0. Next, B1, that is 0. B2 times 1, B2. And this one is 0. 0, 0 plus B3. So finally, we find that the result is identical to what we inserted. So this operation doesn't change anything. As a result, this 1, 1, 1 in the diagonal, this is a diagonal. Every diagonal element is 1, and every off-diagonal element, this is off-diagonal. Any off-diagonal elements are 0, and only the diagonal elements are 1, we say this is an identity matrix. And the identity matrix is ij element. That means first, second, third, first, second, third. So ij, so ith row, jth column. So ith row, jth column. Element is always 1 over 0. If I equals a j, it is 1. If I is not equal to j, it is a 0. So we call it Kronecker delta. This is what we just have computed. Okay, scalar product. We can insert identity matrix. This identity matrix is called metric tensor of the Euclidean space. It is based on the measurement of the length. Any vector squared. It is related to the Pythagoras theorem. It is x squared plus y squared plus z squared. And we'd like to know the magnitude. This is the length. So if I insert identity matrix in the Euclidean space and multiply two vectors in a row and column, then we can measure as identical matrix, identical vector, we can measure the length of the vector, length square. In this Euclidean space, it is a very trivial. However, in Minkowski space, in which the Einstein's relativity is defined, that four-dimensional space that includes the space and the three spatial components. We have different way of measuring the length that is called the proper time. And in that case, a metric tensor is not this in this form. Instead, we will find this kind of a strange form. But perhaps I'm planning to open the ESA extended that includes the Einstein's relativity. So we can consider this one in the next semester if I open if the course is allowed to open. Okay, 11. We investigate the matrix representation of various physical quantities. Express A as a product of two matrices. Okay, this is a linear combination, but 1, 1, 2, 2, 3, 3, repetition, addition. Aha. So we can collect the Cartesian components in this manner. And why don't we collect the unit basis vector in such a manner? In mathematics, they usually do not use it. They have only a single field on which the matrix is defined, but the physicists have a much more freedom. Why not? This is a pure number. They are vectors. This kind of way is also allowed to express a vector. This is another way, but you will find this is a very, very convenient form once you study the rotational operation or any kind of various physical transformation. Find the matrix representation of A in terms of Cartesian coordinates. Okay, we can say these are components. You can write in this form or in a row. That's fine. If I claim this is a vector, I hide the unit basis vector somewhere else. So prove A dot B equal B dot A using matrix. Okay, so this is A1, A2, A3 in row vector and column vector B, Cartesian components, multiplication, first, second, third, and first, second, third, addition. Okay, that's fine. I can exchange the order of the product. So BA, 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 1, 1, 2, 2, 3, 3. Okay, I can put this row vector, so B first, and column vector of A next. So according to the definition, they are identical to this. That's fine. But finally, we define a matrix. Oh, a little bit busy. However, you can find this 1, 1, 2, or 3. And these are 1 prime, 2 prime, 3 prime. Aha. And this one shows that a set of unit basis vectors. And I'd like to introduce another basis vectors a little bit rotated from the original one. We say E1 prime, E2 prime, and A3 prime. If I find out all of the scalar products among them, I can construct a rotation matrix. We will find in the next in detail, but just forget about the origin of this matrix, just carbon copy and compute. And 1, 2, 3, they are satisfying Kronecker delta. As we know, these are unit basis vector of the Cartesian coordinate system. Another set of unit vectors in the Cartesian coordinate system themselves must satisfy the Kronecker delta. It is a trivial. It must. We don't have to prove this. But the problem is that when they are mixed, if I compute the scalar product among them, a little bit complicated. Okay. Explain the meaning of RA. RA. I copied R. I copy this R and multiply A. Let's see what's happening. First, I multiply this one. So E1 prime, everything is E1 prime. That's fine. And then what's next? E1, A1. E2, E2, A2. E3, A3. Okay? That appears repeatedly. Repeatedly. And the scalar product is what? 1 prime, 1 prime, 1 prime, 2 prime, 2 prime, 2 prime, 3 prime, 3 prime, 3 prime. Oh, trivial. Trivial. So I can collect everything all together in here, and E1 prime, E1, A1. This one is the same. What's that? A1 equals E1 hat. Oh, by the way, we have passed 1 minute. So if you follow this calculation, what we find is that identical vector in a new basis in terms of new basis set. So RA shows the components expressed in terms of new basis vector. That is a very important. So this is repeats the completeness relation. Whatever basis you bring in, the expression is always reproducible. That's it for today. Thank you.